Hello, everybody. As Brock nicely introduced me, my name is Marcelo Vanzin. Work for Cloudera in the Spark as an engineer in the Spark team. And today I'm going to be talking about running Spark on Yarn, basically all the features that you can expect from Yarn today and where we want to take the integration of Spark with Yarn in the future. Little outline of what we're going to be talking about. First, little introduction of Yarn, very quick, so that people who are not familiar with Yarn know what I'm going to be talking about. Also, a very quick introduction for why Yarn is interesting for Spark. And then we're going to dive into resource management and security and the current features and where you can expect us to take this integration in the future. So what is Yarn? Yarn stands for yet another resource negotiator. It basically manages all the cores and the memory in your cluster. And it negotiates allocation of those resources to multiple users and multiple applications running on that cluster. Yarn has a bunch of different features that make it very, very interesting for Spark. A few of them, for example, you have a distributed cache where if you have an application jar file, you can load it onto HDFS, and Yarn will automatically distribute that to all the nodes in the cluster and keep it cached, so that subsequent invocations of the same application don't pay the cost of distributing that file. And the same applies to any other file that you add to your application using Spark Submit, for example. It has a preemption, so that if an application is running, but another application that has higher priority comes up, it asks that first application to relinquish some of the resources so that the new application can run more efficiently. And if the application is not playing nice, it doesn't respond to those requests, Yarn just goes and kills that application to give room for the higher priority one. Another thing, it has a very featureful support for queues and nested queues, so you can have different queues with different resources for example, for different departments in your organization and different users within those departments. It has lots and lots of resource management features, such as integration with Linux C groups. So aside from the allocation that Yarn itself does, you can have Linux do even more fine-grained accounting and make sure that applications are only using the amount of CPU that they requested, for example. So why use Yarn for Spark? So we already talked about all the resource management things. So let's talk a little bit about the different things in Spark that make this integration work really well. So we're gonna give a lot of room here for dynamic allocation, which I'm gonna be describing and talking about in detail, and also some security features. Let's look at the resource management problem from Spark's perspective. So right now, when you deploy your application on Yarn, there's a lot of knobs you have to turn. So this is a picture that shows what the memory looks like in a Yarn node manager. So you have the amount of memory that the node manager knows about and can allocate to applications. Within that, you have your executor container that has the overhead memory, which is any memory that is not in the Java heap. You have the Java heap itself, which is the executor memory. And within that, you have different partitions for shuffle and cache data and other things. So there's, aside from this, which is just one executor, you also have to size how many executors your application is going to need up front. And all that is very tasking on the developer, and different applications have different needs, so it becomes a real big burden to fiddle with all these flags to get something efficient out of your application. So that's why dynamic allocation was added to Spark. Basically what it does is it removes the need to specify the number of executors you need in your application. So based on the jobs that you run and the tasks that those jobs need to execute, Spark goes and talks to Yarn and requests new executors. And as your application winds down and executors become idle because there are no tasks to execute, Spark gives those resources back to Yarn so that our other applications can use them. The one downside is that right now you still have to specify everything else. So you still have to specify how many cores each executor is going to need, how much memory those executors are going to use, and everything that is not just the number of executors. So a little example, just a small animation to show how it works today. So basically, if you start your job, it's going to have a bunch of tasks. I'm simplifying a little bit. You have stages within the jobs, but for dynamic allocation, all that really matters are tasks. So as your tasks start to get backlogged in the scheduler, Spark will ask Yarn for executors. So it starts one executor and then assigns a task to run on that executor. And as that task is taking time to complete, it comes and starts another executor so that backlogged tasks can be executed. And so on and so forth. As tasks finish, the tasks that are in the backlog keep assigned to those executors until all the tasks have finished. And as the executors are idle, Spark will give them away to the cluster so that the resources can be reused by whoever needs them. So how can we make dynamic allocation better? So what are the current shortcomings? So I'm going to talk a little bit about allocation latency, because that's a very internal thing. It's basically having better heuristics for when to request those as executors, so that if you have like a really large backlog of tasks, you quickly request more and more executors so that you can get rid of it. And also on the other side, more efficient communication with Yarn, because the communication pattern that you have to Yarn is not very efficient, so you have to control how fast you pull Yarn, how quickly you send information to Yarn so that those executors can come up quickly. We're going to go into a little more detail about data locality because it's important. So right now, the dynamic allocation backend in Spark has no idea about data locality. It's just going to ask Yarn for an executor wherever it is. So what you really want is for the new executors to go where the data that the tasks you want to execute is. So in the end, this gives you a lot more predictable performance. This work is being tracked in 4352, and it was basically triggered by tests that we did when testing Hive on Spark. Basically, every time you execute the same query, we were getting different performance because the executors are being allocated on different nodes that are far away from the data or have no relation at all to where the data is. So this should make things a lot more predictable in Spark with dynamic allocation on. The next problem is cached RDDs. Right now, when executors go idle, Spark will just get rid of the executors and whatever cached data they hold. That's bad, and I don't need to explain why, because the data will have to be recomputed if you actually need it. So the current short-term solution that we have is to keep the executors around. This change is not in Spark 1.4. It's going to be in 1.5. But it basically has a different timeout for executors that actually have cached data. And that can be controlled so that you can keep them around for as long as you need for your application. But in the long term, there are different things that we can do to play with cached data. So basically, if you're not using all the available memory for caching in your cluster, you can basically rebalance the data. Basically send cached blocks to executors that are idle so that you free up some of the executors and can give them away to the clusters. Another thing is doing container resizing. This is mostly so that you can free vcores for the cluster because you can't really resize the Java heap on a running JVM. So that's a very little gain that we see in that. And also there's the ability of using off-heap caching. There has been some work towards integration with HDFS DDMs. This would be something to look at in the future so that you can just kill the executors, but the cache data will still be there. This needs to be integrated with Yarn resource management so that even when the executors go away, your application is still charged for the memory it's using in this off-heap cache. So that's one of the challenges in integrating this work with the rest of dynamic allocation. Given these low-hanging fruit, we thought about after talking to customers, we thought about a few things that we could do in the future to make memory sizing itself easier. So one of the things is support for soft container limits in Yarn. This is not really to make application sizing easier, but basically make Yarn play a little bit nicer with applications when resources are available. So right now, when an application is using more resources than it asked for, basically Yarn uses a big hammer and kills the application, and that's not nice. So with soft container limits, if there are resources available in the cluster, Yarn will kind of not pay too much attention for applications to applications that actually go over those limits, and will let them run until those resources are actually needed. And at that point, Yarn would kill the application. This would let people know if the applications are going over the limits that they requested, so that they can size them better. But in the future, there are things that we can do that can make this even more automatic. So we're going to talk about how overhead memory affects Yarn applications, and we're also going to talk about simplifying those parameters. So overhead memory, as I mentioned before, is everything that's not in the Java heap. So you have native library buffers. You have the Yarn the Java permgen. You have direct buffers used by Java libraries, and all other things that are really hard to figure out where that memory is being used. So the first thing that we need here is to understand where that memory is going so that we can make smart decisions about when we need that memory. So we have plans to build better metrics and better tools to figure this out. And with those metrics available, we can develop better heuristics in the dynamic allocator so that it can make smart decisions about how much overhead memory to request from Yarn. So that if you're running an application that actually needs more native heap, the dynamic allocation backend can detect that and automatically figure out that parameter for you without you having to iteratively increase that value until your application stops dying. And in the future, where we want to take this is a world where you can define a task size for your application, for example. Basically, a single parameter that defines how big your application is. And the dynamic allocation backend is smart enough to take that value and maybe do some runtime analysis of the data that your application is processing and be able to figure out all the other parameters for requesting containers from Yarn. And this can lead to all sorts of different optimizations about container sizes. So you can say, if your data is skewed in such a way that certain blocks are stored in a few nodes, you can request large containers on those nodes, while in other nodes where you don't have that many blocks, you can request smaller containers. And thus make more efficient use of the resources available in your cluster. So I think that's it for resource management. So basically what our goal for the future is having dynamic allocation be enough for most applications. There's always applications that are not going to be able to use dynamic allocation because of very strict SLAs and other characteristics. But we want it to be good enough that people will only think about disabling it when an application really, really needs it. And by the way, this code is paraphrased. If you can recognize where it's from, kudos to you. So let's move to the next topic, which is security. At first, we're going to talk about Kerberos. So Kerberos is used in Hadoop generally to do user authentication. All Hadoop services support Kerberos. So basically, you can log into Kerberos, and then you can use your Kerberos ticket to log into HDFS, HBase, Hive, and all other Hadoop services. And the way that this is done is by using per-service delegation tokens. But what are these? So delegation tokens are a way for applications to avoid running into KDC limitations. So if you don't have delegation tokens, what you would need is every executor in a Spark application, for example, would need to log into the KDC to get a Kerberos ticket and use that ticket to talk to the service. As soon as the KDC sees like 100 executors asking to log in as the same user, it's going to think that something is wrong, and it's going to start denying logins. And you do not want that, because then the executors would not be able to talk to the services. So instead, you have a single process, which I'm calling the driver on this picture, that talks to the KDC. And with the Kerberos ticket that it gets from the KDC, it talks to the specific services it needs to access, gets a delegation token, and that delegation token is distributed to the executors. So the driver process is not necessarily the Spark driver, which is going to be come into play in the next few slides. It is generally the actual process that launches the application, which if you're running in Yarn cluster mode, for example, is not the driver. So one thing that delegation tokens and also Kerberos tickets have is a TTL. They have a maximum time to live, and after that TTL, those tokens and that ticket are not valid anymore. This is a very big limitation for long-lived applications such as Spark Streaming, or if you think about the Spark SQL Thrift server, because you want those applications to be available all the time and running, and you don't want to have to restart them every once in a while just to get new credentials. So the solution here is to regenerate the tokens periodically. The way this is done is that you have the actual application running, in this case the driver, relog into the KDC every once in a while and request new delegation tokens from the services and distribute them to the executors. So this was not possible with Spark 1.3 because you had no mechanism to redistribute the user credentials to the cluster. But the support was added in 1.4, and you can distribute the user's key tab in Yarn cluster mode, and it will take care of regenerating delegation tokens every once in a while, redistributing them, and so basically enabling long-lived applications in secure Yarn mode. And if you couple this with encryption both in HDFS and in Yarn, you basically have a secure communication channel to just distribute these credentials, so you don't need to worry about someone sniffing over the traffic and seeing those credentials. The next thing about security is encryption. So basically making sure that nobody can see the data that's flowing within your application. And if you look at encryption in the Hadoop ecosystem, HDFS supports it both on the wire and also at rest. Yarn supports wire encryption, but Spark has kind of spotty support for encryption if you look at it. What are the different places where Spark would use encryption? So you have the control plane, which is basically the communication between the driver and the executors. You have file distribution, which is anytime you call Spark context add jar or add file, those files are distributed to the executors using a small HTTP server running on the driver. You have the block manager, which is the part of Spark that distributes the shuffle files and the cached blocks, and also broadcast variables. You have the user UI and the REST API. Both are an HTTP server running on the driver. And finally, you have data at rest, basically the shuffle files generated during shuffles. So the goal that we have for encryption is to make it as easy as possible to configure, so that you basically don't need to think about it. So that means using SSL for HTTP endpoints because you want to be able to access those endpoints using a browser. And using SASO everywhere else because SASO is very easy to configure. Basically, there's no configuration. In 1.4, what do you have? You have SASO for shuffle data. Basically, all the communication of the block manager can go through encrypted SASO. And you have SSL available for Akka, which is the control plane in 1.4, and the file distribution HTTP server, but not the UI HTTP server. What does it take to add encryption to the Spark UI? So basically, you have this Spark Jira tracking this work. It's not complicated to add support for SSL in the Spark UI, but there are outstanding issues with distribution of the certificates, especially in cluster mode, because the file needs to be available on the node where the driver is going to be running. And also, there's an issue with shared certificates, because if you have everybody in the cluster using the same certificate, basically everybody has each other's private keys, so it's not really as secure. Another thing that we're thinking about the Spark UI is maybe we don't need to encrypt the Spark UI. If we just audit the code so that we're sure that there are no sensitive information being displayed in the Spark UI, maybe it's OK to just not encrypt it. Or if people are really paranoid about it, you can disable the Spark UI altogether. The second one is the Spark RPC, basically the control plane. Currently, you have Akka over SSL, so it has all the problems with certificate distribution and shared certificates. In the future, there's work being done to replace Akka with a Spark RPC-based framework. And that framework can work over SASO just like the shuffle, the block manager RPC works over SASO. And if you care to follow these issues, those are the two JIRAs. And sort of related to this, you have that little HTTP server that does file distribution. The RPC library used in Spark was built mainly to cover the use case of distributing shuffle files, so it's very efficient at distributing files. So it should be very easy to replace this HTTP server with the RPC interface, and does have support for SASO encryption on top of it. Next is data at rest. So data at rest, basically shuffle files. There's not a good solution today. Basically, you have to go outside of Yarn or Spark and actually configure local file systems to be encrypted if you want to encrypt these files. And then you have to go and change the Yarn configuration to point the application scratch space to use these encrypted local disks. In the future, we want Spark itself to encrypt these files so that you don't need to do this extra configuration step, and also to have a little bit more security by having different applications use different encryption keys for those files. Data at rest, I mean, this data never really goes over the wire, so it's mostly for people who are really, really concerned about the actual physical disks being accessed by someone else. But it's something that certain customers really, really care about. So I went a little bit faster than I expected. I already got to the end. So basically, what I wanted to convey is that Yarn has a lot of useful features, and Spark makes use a lot of a lot of those features. But with all these features, there's a price, because it's not really easy to use all of these features. So in the future, what we're trying to focus on is mainly usability, making sure that it's easy to use Yarn, that people can deploy their applications easily and bring them to production in a timely manner. And also focus a lot of security, because that's very important to a lot of customers. But never forgetting to look at performance also, because that's one of the reasons why people switch to Spark in the first place. So I guess that's all I had. So thanks for attending, and I guess we have some time for questions now.
I have a question.
Sure, go ahead.
Well, I didn't know asking a question, getting an applause. But I have a question. We're using Spark on Yarn, and we have a problem of the last couple of tasks hang there without error message. It just hang there forever. And this same code would work fine on a standalone cluster. So we looked online and found that people reporting the same problem after they changing the block transfer service from the default NATI to NIO, and then it works on Yarn. We're surprised of slower performance and many more fails and retries. So I wonder if you have any insights on this particular problem.
This is actually,
I'm sorry, this is on Spark 1.2, and people are reporting they see this on 1.3 as well.
This is actually the first time I'm hearing of this problem. So if you can send me more information or send information to the list, I'll definitely take a look at it. But this actually comes as a surprise. I was not familiar with this particular error.
What are your plans for supporting secure Hadoop impersonation using Yarn on Spark?
Spark already supports impersonation. There's a parameter to Spark submit that if you have configured proxy user support in Yarn correctly, you can ask the application to run as a specific user.
Can you also do that via the Python or Scala APIs?
No, those are not available through the programmatic APIs. They have to be done through Spark submit currently.
Thanks.
OK, I'm going to ask. So I just want to clarify on the dynamic resource allocation feature. So a lot of cases, you're involving a number of executors as well as the memories. So your dynamic resource allocation apply to the memory or not?
Currently, it does not apply to memory. Currently, dynamic allocation is solely based on the number of executors needed to go through the backlog of tasks.
I see. So just another different question. So for long-running Spark job on Yarn cluster mode, is there going to be any problems? Like if you keep the container staying there for a long time?
There shouldn't be a problem with the containers being alive for a long time. The only problem is if you're running Yarn in secure mode, as I mentioned. You can only do that for more than 7 days if you're running Spark 1.4, and you supply the new parameters to actually provide the user credentials so that the driver can relog in.
Thank you.
How many of the features that you've discussed today really apply just to Yarn? How many should be applicable to any workload scheduler for Spark? And like how are you deciding when to do it in Spark and when you're doing it in Yarn?
So most of the features, I guess, apply to any scheduler that allows you to bring up executors on demand. I think that there's a patch to add dynamic allocation support to Kerberos, for example. Some of the things that I talk about are kind of Yarn specific. For example, the overhead memory. I don't know how other cluster managers use it or if they have that concept at all. But that's something that matters to Yarn because when you request an application, when you request a container, you basically ask for a container size. You ask Yarn for 1 GB of memory, and then you have to decide how much of that memory you're going to use for Java heap and how much you're going to use for the rest. So that's one thing that Yarn might differ from others. But in general, unless I specifically called out something that needs to be done in Yarn, it's something that should apply to any cluster manager that can bring up executors and bring down executors on demand.
Guess I'm good. Is dynamic resource allocation for Spark streaming on the roadmap at all?
It's something that we have thought about. Spark streaming has some particular characteristics that may require some different heuristics for efficiently allocating new executors. We have some ideas that we want to try out to make sure that the existing code can be used with certain parameters to not make anything worse for Spark streaming applications. But at this moment, at least us in Cloudera, we are not looking specifically to write code for Spark streaming in dynamic allocation.
So when we run Spark jobs on Yarn cluster mode, we specify saying that the executor memory should be 2 GB, or we can specify that. But when we see on the Spark UI, the executor has roughly half the memory. Can you talk more about what happens, to the memory?
So the memory that you see on the Spark UI is actually the memory available for caching RDDs. So by default, that's 0.6 of the executor memory. So that's why it's about half.
And what else uses the other half of the memory, like the 40% of the memory that is there?
So basically the way it works is if you're using the feature where you cache RDDs, cached blocks from RDDs, it's going to use up to 60% of the heap for that data. And after that, it's going to start evicting data from the RDD. So basically 40% is reserved. I mean, there's no actual mechanism to make sure that the rest of the data is not going over that limit, but the 40% is reserved for everything else that your application is doing.
Hi, my question is there any plan for opening up the programmatic API to submit the jobs to the Yarn? Right now, there is some private API, but not public API, and I see a lot of encouragement submitting jobs through the Spark Submit command line, but we have application where we want to submit the jobs from web application.
Mm-hmm. Yes, there is some work that I don't know if anybody else was working on it, but I've been spending some time to enhance the Spark Launcher library to allow more fine-grained control of the applications that are launched. And that should play nicely with submitting applications to Yarn and monitoring them and make sure that they're running and interacting with them.
Hi. Sorry.
Hi, I think we have time for one more question.
So if you want to run like Spark on Yarn cluster after job has completed, like what is like future of Spark? Will you go developing more on Spark UI, or can we see completed like jobs on like Yarn job history? So we can have just one UI for all completed jobs if we are running, let's say, Hadoop MapReduce jobs. So we also see Spark completed jobs on Yarn cluster like job history.
I see. So the current Yarn history server doesn't support anything other than MR applications. But Yarn has this feature called the Application Timeline Service, which provides support for any application to write history data to Yarn. I don't think at the moment it supports custom UI, so you still would need the Spark history server to look at the actual Spark UI. But the data itself can be stored in Yarn and processed using Yarn's API. That support's still not in Spark. Some of our friends at Hortonworks have been looking at it. There's a PR open. We just need people to look at it and review it.
That's all the questions.